Well, welcome back to Remote Sensing Applications using ArcGIS. With climate warming in Alaska, winter rain events have become more common in boreal Alaska. And these rains often lead to extensive canopy icing and high winds, leading to the mortality of large white spruce trees in interior Alaska. These tall white spruce trees can be hundreds of years old, and therefore they're scientifically important because our climate station record in boreal Alaska is sparse. And using tree rings, we can infer the climate back hundreds of years beyond what we have based on climate station data. So in this mini project, you could use repeat LIDAR to estimate where all the tall canopies were in 2004 and locations where those tall canopies no longer exist in 2014. And those would be locations where tall white spruce trees have suffered mortality and wind throw. So as a first step, if you go to the Blackboard website, this is mini project 7, and you'll download the LIDAR data from 2004 from this file, repeat LIDAR zip data. So here we have a polygon representing our study area and an ortho photograph of a white spruce stand within our study area. And then you'll have a raster representing the canopy height in meters in 2004. So then from this raster, which was derived from LIDAR, we could pick out all those pixels that are taller than 33 meters in canopy height. So that gives us a raster of tall pixels, and if we look at the attribute table, we've got 134 pixels that have a canopy height above 33 meters. Now, some of those pixels may be from the same individual white spruce tree, so then what we'll do is we'll group these into separate groups using the region group geoprocessing tool. And that gives us 80 different groups of tall pixels. So we could sort the count of these groups descending. So for example, here's a group of 5 pixels, and these 5 pixels all have their tall pixels, and they're all above 33 meters in height. So then what we could do is we'll convert our tall groups into polygons based on the value. So take our groups of tall pixels and convert those into polygons, and we'll name that tall patches. And don't simplify the polygons, retain the square shape of our original pixels. So for example, here is a tall patch polygon, and it has an area of 5 square meters. So each of these cells is 1 meter squared. And if we zoom out, you can see that indeed it is a white spruce canopy. Okay, so we've got polygons representing canopy height above 33 meters. The next step is we'll create points at the center of each of these polygons. So we can use the feature to point tool and make sure you have inside checked on. That uses a location contained inside your polygon. So that will give us the tall locations in 2004, basically the centroid of the tall patches. So for example, here is the tall location for this individual patch in 2004. Okay, we're going to use data from the G-LIGHT, which stands for Goddard's LIDAR Hyperspectral and Thermaging Imager. And that's an airborne instrument that was flown in boreal Alaska in 2014. So it's going to be fairly high resolution. We're interested in this application, just the LIDAR data. So if you go to the data link, and then go to downloads, and then either of these will get us to the map interface we're interested in for downloading. So zoom in on the area near Fairbanks, and we're interested in this data set, Glen 300 kilohertz, 11 August 2014. And when you click on that bubble to the right, you'll have an acquisition list. And we're interested in the canopy height model in GeoTIFF. So that's going to be the canopy height in meters within our study area, which is part of this data set Glen 300 kilohertz. So we'll download that GeoTIFF, and it's 7 megabytes. And I will download it as a packaged document. So, and then here's our download link. So that's going to be a tar file that we're going to unzip. So I'll save that, and then we'll unzip that file. So show in folder, and then right mouse click, 7-zip, or whatever you use to extract your file, and we'll extract it. Okay, so then if we go inside this folder, and then the metadata has a PDF about the data. If you go inside the LIDAR folder and then GeoTIFF folder, here's the actual LIDAR canopy height model, and it's gzip, so we'll have to unzip that. So that gives us this TIFF, which is going to be the canopy height model for 1 meter pixels in 2014. So we can add that to our ArcMap document. And now we've got the canopy height model from 2014. So the first step will be take our study area and use that to cut out the LIDAR data within our study area. And then the next step will be to take this raster that's been cut inside our study area and create a raster representing all those pixels that have a canopy height above 33 meters. So that gives us 1,223 pixels that had a canopy height above 33 meters. So next we'll group those to get groups of pixels that have a canopy height above 33 meters in 2014. And that gives us tall groups in 2014. There's 193 tall groups, and some of them are up to 20 pixels that are connected, and those 20 pixels all have canopy height above 33 meters. So the next step is we'll convert these tall groups into tall patch polygons and then derive the center of each of these tall patch polygons. So we should have 193 locations for these tall patch polygons when we're done. So as a check, we could use these tall patches in 2014 and use the zonal statistics as table. What's the minimum canopy height inside each of these tall patches? So there's 200 polygons representing the locations of tall patches, and inside those 200 polygons, the minimum canopy elevation is always greater than 33 meters. So if we look at all the minimums from these 200 patches, there's one that's 33.0099 meters in elevation. And then we'll get the locations of the centers of these tall patches. Okay, there's going to be some horizontal error in the locations of the LIDAR in 2004 and the LIDAR in 2014. So for example, here's a tall patch in 2004, and here's a tall patch in 2014. And they're likely from the same white spruce tree because these are 1 meter pixels. So if the location from the center of the tall patch in 2014 and the center from the tall patch in 2004 are fairly close to each other, well, that probably does not represent a location where the canopy of the tree fell down due to winter rains. So our final step is to run the near tool for each tall patch in 2004, go out and find the closest center of the tall patch in 2014. So for example, this same location The distance between the tall patch center in 2014 and the tall patch location in 2004 was 1.5 meters. So you'll have that for all 91 tall patches in 2004. So we're going to consider if the distance is 15 meters or greater, that likely represents a location where it was a tall white spruce tree in 2014 and it suffered canopy damage by 2014. So select all the locations that have a distance beyond 15 meters. So greater than or equal to 15 meters. For those points that have a distance greater than or equal to 15 meters to a tall patch in 2014 compared to the tall patch in 2004, for those locations, project them into longitude and latitude, and then use the add XY tool to get the longitude and latitude of those locations. So project them into longitude and latitude NAD 83, and then use the add XY tool to get the longitude and latitude of those locations. And then email me a table representing the longitude and latitude of these candidate locations that we could visit to look for, did indeed a white spruce tree exist at that location and is now a wind-thrown white spruce tree.